So let's talk about the Wittig reaction. Now the Wittig reaction involves the formation of the Wittig reagent, which then goes on to react with a carbonyl to form an alkene. So in these two examples, what we're essentially doing is taking the alkyl group from the carbonyl and the alkyl group from an alkyl halide and stitching them together with the help of the Wittig reagent. So why is this reaction so useful? Well, basically it's because we can form a carbon-carbon double bond in a very specific location and configuration. So let's see one example that highlights its importance. If we have this alcohol right here, which is secondary in nature, but it's directly adjacent to a quaternary carbon, what happens is, if we react this with strong acid, sulfuric acid, and set the reaction to 160 degrees, we get this product here, which is the result of methyl shift from carbon 3 to 2. This alkene is the Zaitsev product. So we can't necessarily control the formation of the double bond when we use sulfuric acid and set it to 160 degrees, which means vigorous conditions offer less control. In the Wittig reaction, this doesn't happen. No rearrangements occur. And the general idea of this reaction is we can stitch together alkyl groups in a very specific manner, not only in terms of where it occurs, the regiochemistry, but also, and more importantly, the stereochemistry. So here's the general effect of the Wittig reaction. If we start with a general carbonyl structure, like this, where R and R prime could be the same or different, it could also be an aldehyde. But if we send this through the Wittig reaction, what happens is the carbonyl backbone does not change, but instead of the carbon-oxygen double bond, we form a carbon-carbon double bond. So to do that, we need triphenylphosphine, which is refluxed with our alkyl halide in toluene. And then in the second step, we need a very strong base, such as N-butyllithium, which also must occur in an aprotic environment, so THF works just fine. And because of this, we transform the carbon-oxygen double bond to the carbon-carbon double bond in the exact same position. That's why this reaction is so useful. I think understanding the reaction mechanism is the best way to understand where this carbon-carbon bond is coming from, as well as the stereochemistry and what factors determine that. So the primary determining factor for the stereochemistry, Z or E, is the stability of this phosphonium ylide, which derives from triphenylphosphine and our alkyl halide. So as a general rule, the more stable the ylide, the less reactive it is, which means we have greater thermodynamic control on the reaction. So if we have a more stable ylide, we form the more stable alkene. And the converse is true too. If we have a reactive ylide that is not stable, it's unstable, we form the Z alkene, which is the less stable analog of the E alkene. So let's see what differentiates stable and unstable ylides with the reaction mechanism. So in step 1, we reflux triphenylphosphine and our alkyl halide to form the phosphonium salt. Now this is the structure of triphenylphosphine, which has importantly a lone pair on the phosphorus, which makes it a good nucleophile. Now as a nucleophile, what it can do is attack the carbon on the alkyl halide that bears the leaving group, that bears this halide. So triphenylphosphine attacks that carbon, sends off the leaving group, and we form this compound here, the phosphonium salt. Then in step 2, we use a strong base like N-butyllithium. Now this carbon here essentially bears a lone pair, which can acquire a proton or function as a nucleophile. Well, here it functions as a very strong base, and it's abbreviated B-. So this base comes here and plucks off this alpha proton, where it's alpha relative to the phosphorus. So it takes off that proton, and what happens is we neutralize our base, and we form the phosphonium ylide. Now here's where stability comes into play. It's the delocalization of charge, in which we spread the charge over a greater area, that determines the reactivity of this ylide in the Wittig reaction. So here, even though this resonance form is showing, there is no delocalization of the charge. And because of the charge disparity, the negative charge on this alpha carbon remains. This ether portion is too far away to participate in any sort of resonance. So essentially, this phosphonium ylide is very reactive, and the charge is concentrated on this carbon here as a result of deprotonation. That's where we add the carbonyl to form this strange-looking square compound called oxaphosphatane. This ylide is nucleophilic and will attack the partially positive carbonyl carbon in the carbonyl system. So the nucleophilic carbon comes in, attacks the carbonyl carbon, sends electrons up to the oxygen, which is already partially negative. And that partially negative oxygen is attracted to the fully positive phosphorus in this ylide right here. So we form an oxygen to phosphorus bond, shown right here in red. And this red arrow, which was the nucleophilic attack, establishes the carbon-carbon bond that we see in the alkene. So that is where the double bond comes from, this nucleophilic attack. And that's shown right here in red. Now all we do is add our substituents. So coming off of the carbonyl carbon, we have the isobutyl group. And off of the nucleophilic carbon, we have a methylene group and then a methoxy group, which is shown here. Now the reason they're cis is because this reaction occurs very quickly. And because it's a quick reaction, that means our ylide was very reactive. So that is where the stereochemistry is established. Now step 4 is olefination, or the formation of our alkene here. How does that happen? Well, two things need to occur. We need to form the pi bond as well as get rid of this upper portion of oxaphosphatane of this square. So if we get rid of the top portion and retain the bottom into our alkene, we'll form our Z-alkene and our stable compound. Now you'll notice, this compound here is an inorganic phosphate analog. So we know in biology that phosphate occurs in all living systems and looks kind of like this. Now because phosphorus can expand its octet, this is actually a stable structure, aside from the reactivity of these oxygens. So it would follow that if we replace these oxygen atoms with phenyl groups, the stability is increased. So to strive to form this stable phosphate analog, the ring must close in this kind of manner to form the oxygen to phosphorus double bond right here. And this upper portion just leaves the compound. It dissociates. At the same time, we form the carbon-carbon double bond with this kind of closure right here. And because these two substituents are cis, we form the Z-alkene. So if we go back here, we essentially stitched these blue carbons and this red carbon alkyl group together in a cis configuration because our ylide was reactive. Now what if we have a stable ylide? That's where mechanism B comes in. Essentially the first two steps are the same. Triphenylphosphine attacks the carbon bearing the leaving group and we form the phosphonium salt. The second step is also the same. We come in with a strong base, the alpha proton is plucked off, and we form the phosphonium ylide. The ylide is where we have positive and negative charges directly adjacent to one another. Now this ylide is able to disperse the negative charge over a greater area, which is essentially the goal of resonance. Resonance attempts to explain the stabilization of a compound based on charge dispersion. Let's look at this lone pair right here on the nucleophilic carbon. Well, it has two different paths going towards the left and right. If the lone pair moves towards the right, it establishes a pi bond, which would then force electrons onto the oxygen to form this minor contributor. However, the major contributor is where we have no charge, and that happens when this lone pair moves towards the left and establishes a charge-less structure. But really, the story of stabilization is explained by this minor contributor, which is telling us that this negative charge can be dispersed all the way up to this ester oxygen right here. This negative charge is not concentrated on this carbon alone, and instead can be spread over a larger area, which confers more stability. So it would follow that if we have a stable ylide, it isn't as reactive, and the reaction occurs slowly. So similarly, the nucleophilic carbon attacks the carbonyl carbon, which sends electrons up to the carbonyl oxygen, which is then attracted to this partially positive phosphorus. The square oxaphosphatane also results with stable ylides, and it closes the same as well. But in this case, the benzene group coming from benzaldehyde and this ethyl acetate group coming from our former alkyl halide are trans to one another. And that's where our E configuration originates.